Welcome to ICDD's InSession webinars and Dr. Paul Bartholomew's presentation, the ICDD Raman File, Design, Content, and Applications. Please remember to visit icdd.com for information on free webinars, educational events, PDF databases, and JADE software.
Good morning, everybody, at least those of you in a U.S. time zone. Quick outline of what we're going to be talking about today. I'm going to start with the principles of Raman spectroscopy. At this point, it's still not a universally known technology, so we're going to quickly go through that. And yes, I'm a mineralogist. The initial release of the Raman file is on minerals, but the principles apply to crystalline materials. Some of the principles apply to Raman of liquids and gases as well. Then we're going to look at the Raman file content, its design, and the process of populating it so far, and results that have been achieved so far, plans for the future, and then a couple little demonstrations. All right, so the principles. The Raman effect is connected to the quantized energy levels of interatomic vibrations. Same phenomena happens in a crystalline matrix. Vibrations just have a little fewer degrees of freedom. Like any spectroscopy, we send us a exciting signal to the sample, in this case, visible light, and yes, into the infrared, and it can be into the ultraviolet as well. The kind of things that can happen, the most common interaction is the vibrations are absorbed a photon or raised to an arbitrarily high state, fall back to the ground state, and release a photon of the exact same wavelength. In some cases, when the energy of the photon matches one of the elevated energy levels, it's simply absorbed. That only really happens in the infrared, and hence infrared spectroscopy. In some cases, elevated to excited state, and then dropping down to a state above the ground state. And so the resulting photon has less energy. The difference is called the Raman shift. With infrared, we hit the sample with a broadband source and look at which wavelengths are preferentially absorbed. With Raman, we need a monochrome source in order to see the size of this Raman shift. All right, how do we do this? Schematic here, our monochrome source is generally a laser. Generally, there's a cleanup filter so that only one wavelength is carried to the sample. And then there's optics to pick up the scattered light and send it into a spectrometer. And then a very important component here it's labeled long pass filter. We refer to it as the laser cutoff filter. Its job is to filter out the Rayleigh scattering, the light that's at the same wavelength at the laser. And at the same time, it has to pass wavelengths very close to that wavelength. So it has an important job. The resulting instrument, here's a research grade Raman microscope, and at the same time with diode lasers and CCD detectors, there are Raman spectrometers that are handheld. All right, let's look at what the result looks like, some Raman spectra. These three spectra are also all of polymorphs of SiO2. Right away, we can see that different structures give us different spectra, different sets of peaks. So already we can see how this can be used for phase identification. What are we seeing here? The x-axis here is Raman shift. Over here at 0, this is where the laser is. Doesn't matter what the wavelength of the laser is, because all we're measuring is departure from its wavelength. And then over here where the spectrum starts, that's the limit of our spectroscopy given by the laser cutoff filter. Below that limit, the cutoff filter is erasing the signal. Where the peaks are is a function of atomic masses, bond lengths, bond strength, and local symmetry. And so it reflects the structure. it can't be used to determine all the despacings and the actual placement of atoms like XRD, but it is a reflection of the structure. All right, the business of collecting Raman spectrum. All right, we have to do our sample preparation, presentation. We have to choose our analytical parameters, including spectral range. What range of Raman shift we're going to look at, what laser we're going to use, what laser intensity we're going to use, how much time we're going to spend collecting data. It's important to have some familiarity with the Raman systematics of your subject matter. And I always take particular advantage of Spectrum Preview. Many instruments in their software have what's called a real-time or live time, which refreshes regularly and helps you get an idea of what kind of spectrum you're getting and what your counting time laser intensity going to need to be. Raman sampling. Raman is possible with sample prep in some cases. You can take one of these portables out in the field, just hold it up to a rock. It's non-destructive. Not in every case, we'll talk about that later, but that's, it makes it particularly good for working with gems because it's non-destructive. It's optical, so it can look through a window, so we can determine the phases inside fluid inclusions. We can look at phase transitions in a diamond anvil cell. And for you geologists, we could look at phases that are under a cover slip on a thin section. As far as sample prep, we can do it with no prep in many cases, but if we're doing microscopic work, we need a flat polish because we're using microscope objectives with a very shallow depth of field. Spectral range. What are our parameters here? So here's Raman spectrum of gypsum. You can see there's a group of peaks over here, the left between 100 and 1300 wave number. That's kind of the fingerprint region. And then they have this OH, H2O stretching peak out here. And there's a lot of hydrous minerals that have OH, H2O. However, they all have peaks in this lower range. None of them have only OH or H2O peaks. So for phase identification, we don't need to go way out here. We only need this region, fingerprint region to the left. How much of it we need, having looked at many minerals and seen the range, here's an example. Sylvanite, its strongest peak is right about 100 wave numbers. Diamond, its only significant peak is out here between 13 and 1400. So we need to go, if we can get below 100, that's great. We need to get up to about 1400 for minerals. Other subject matters, well, we'll have to look at what are the possibilities. All right, choosing laser wavelength. There's a couple of things to consider. Looking at this scale here, you can see this is wavelength, not Raman shift. The black line is relative signal strength. So when we have a shorter wavelength laser, we get a stronger Raman signal out of the same sample. These color bands, however, is how much of the spectrum the spectrometer needs to look at in order to see 1500 wave numbers of Raman shift. And you can see as you go to the shorter lasers, the spectrometer has to work with a smaller and smaller section of the wavelength spectrum. So shorter wavelength lasers require higher technology spectrometer, and often the cutoff filter becomes a limiting factor as far as technology. But our considerations for wavelength are not just signal strength. One of the more common challenges in Raman is dealing with sample fluorescence. When it happens, it can be very strong compared to Raman. Here we see the Raman spectrum of willemite, a zinc silicate. Here with a 532 nanometer laser, the fluorescence is this is even scaled down so you can see both of these in the same graph. The fluorescence has almost completely washed out the Raman signal. Second one down here is from a longer wavelength laser, 7 or 8 nanometers, and we get a good complete Raman spectrum. So sometimes our choice is driven by fluorescence. What causes fluorescence in minerals? Manganese and other transition metals. The fluorescence in wilmite is actually a replacement of some of the zinc by manganese. Rare earths also very commonly. And when we run into that, our first defense is to change the laser wavelength. And so that's one of the reasons a research grade Raman instrument has more than one laser, so you can make that choice. Laser intensity and counting time. Here we have a trade-off. And again, this is for minerals. This graph on the left, the most important thing to look at here is relative signal intensity from different mineral species ranges from 0.1 on this scale to 1,000 on this scale, literally 4 orders of magnitude. So you have to be prepared to deal with a wide range of signal strengths. However, if you are looking at one of these minerals over on the left end, getting enough signal strength, your temptation is just to increase the intensity of the laser so you get a stronger signal. But at some point, the laser intensity can increase to the point where you break down the material. You can see this hole drilled in this example to the right. Some minerals are very sensitive to laser. Many of them are not very sensitive. Again, it's partially knowing your sample material. All right, so the spectra we get, their characteristics. Some of them have very sharp peaks. Some of them have very broad peaks. Common for them to have overlapping peaks. So for phase identification, whole spectrum matching is the standard. Also, for minerals and other crystalline materials, relative intensity of the peaks can vary considerably with crystallographic orientation relative to the laser. Here there are 3 spectra from the same grain of this mineral agerine. And if you look closely, you can see they all have the same peaks. It's just in one they're strong and another one they're weak. Accordingly, your phase match scoring algorithm needs to emphasize peak position more than peak intensity for its matching. And quick look at what the result looks like. You've got some matching program. It runs some similarity index, shows you the results in order of highest similarity to lowest. We're actually going to look at this example later on. I'll come back to it. So those are I should stop and say this, of course, the topic of the day. Your ability to do this pattern match phase identification is limited by your database coverage. So that includes the principles section. I'll just add, if you want to know more about the practicalities, Jeff Post and I have written this document. And again, it focuses on minerals. Many of the principles apply to other materials. It's open access. It's posted on Mineralogical Society website. It's also posted on the ICDD website and their Raman page. All right, reference database. A quick look at what is the ideal for a reference database. Number one, dependability, meaning there should be a high probability that the database contains reference spectra for the minerals in your sample. If it doesn't, just isn't going to work for you. 2, the spectra should come from fully validated mineral species. Both their structure and chemistry have been measured, so we know exactly what phase this is. Ideally, there's analytical assistance in the form of experimental metadata so that people can look at what's in the database, look at the experimental metadata, and drive their own operating decisions based on what they're going to be analyzing. Ideally, ongoing growth so that it does become representative of all the possibilities and even keeps pace with growth in the field. And of course, longevity. You don't want to be using a database and being dependent on it and having it disappear in 5 years. And you want, ongoing support for data quality improvement and so on. Now, ICDD has a deep track record for providing analytical experimental metadata, ongoing growth and longevity. And one of the questions I needed to answer is, can dependability be achieved in some time span other than what it would take to put all 6,000 plus minerals in the database? A quick look at pre-existing Raman reference databases. I'm not going to list them all, but I've kind of grouped them conceptually into a couple of groups. First, there's proprietary databases. They are offered by for-profit companies. Some of them are offered by the instrument makers, and they're only available to buyers of their instruments. In my experience, they have limited content and may not be increasing in their content. Public databases, free databases. There's the user-driven type, the kind of wiki type, good example, the Raman Open Database. And here my experience is there's little incentive for content growth, and it doesn't seem to be a lot of quality management. There's funding insecurity. Again, who knows how long it's going to be there, and it's not set up to actually do any of the pattern match searching. Another one of the public databases, I label it as PI driven, the Rough project. The PI here is Bob Downs at the University of Arizona. He created and started this, continues to exist, not even now he's emeritus. Some of it's, I don't want to call it limitations, as you'll see in a moment. Its content growth is driven by research priorities, and it's not designed around any specific application, such as phase identification. It too has funding insecurity. And it's worth saying the Rough project is the largest by far and the best pre-existing database. And that's important because we have been able to use data from Rough as part of getting the ICDD Raman file started. So the ICDD Raman file, again, one of our first challenges, can we achieve dependability quickly? Of course, yes, our long-term goal is to get some Raman spectra for all known minerals and even collect as new minerals are described. But in a short time, can we provide real practical support for a large percentage of geoscientists? My approach to this was to quantify a concept I call likelihood of encountering. And the most important body of data for this are locality counts from MinDat, the largest online mineralogically database out there. And it's not just the list of minerals, it also lists the localities that these minerals have been found on. And here's an example from these locality counts, starting with the highest locality count at the top. The highest is quartz. Yeah, no surprise. It's extremely common mineral found virtually everywhere. But if you look, number 3 on this is gold, which is clearly anything but a common mineral. But it's high on this list because humans are going out of the way to seek it out. So in this way, we capture both how common and how much geoscientists are going out of their way to seek this out. Also, our modern technology has us looking for, mineral targets, commodities that we have not prioritized in the past. To pick that up, I also included the minerals from a USGS paper on critical and strategic minerals. I also used a list of minerals considered rock-forming minerals to increase the extent to which likelihood of encountering represents common minerals. Having done them, Having done that, I sorted by most likely to least likely, and yeah, it's somewhat arbitrary, but I do think it has a good chance of serving a high percentage of scientists. The initial target is the top 600 most likely. All right, like I said, we got a leg up from the rough um, project, the rough database, which has over 8,000 spectra representing over 2,000 minerals. However, like I said, it's a scientific database. It contains some spectra that they're just not reference spectra. They are real spectra of real materials, but not necessarily reference spectra. Um, because some are spectra from samples that are not completely characterized as to their phase identity. Some spectra do not have a high signal noise ratio. Some of them have spectral artifacts. The content is missing some important minerals and highly redundant in others. So for reference spectra, I needed to curate reference spectra out of rough. My first consideration is to take only spectra from fully verified minerals. Number two, signal to noise ratio. Here you can see examples with signal noise ratio of 20, 50, and 100. You can see the difference as far as definition of peaks. Again, a little bit arbitrary, but I chose a minimum signal noise ratio of 80. Anything from rough below that I excluded. Redundancy. Here you see 4 of the 22 quartz spectra in rough. They're spectroscopically identical. We don't need them all. So I ran a similarity index calculation for pairs of spectra from the same mineral species. High similarity meant redundancy. And when I saw that, I discarded the one with the lower signal to noise ratio. Non-Raman artifacts. Here's an example, 2 spectra of the mineral cuspidine, 532 from 532 and a 780 nanometer laser. You can see some peaks are the same and some of them are different. In fact, the ones that are strikingly different are from neodymium fluorescence, which is a non-Raman artifact. Detecting this, um, I just had to visually compare spectra from the same species to look for these kinds of artifacts. And yes, some familiarity of where fluorescence pops up was required, but that, yeah, that was a lengthy process. All right, so this curation process resulted in rough spectra covering 363 of the top 600, leaving me with covering the other 237. So I needed to collect Raman spectra for these. Pretty straightforward process. You get samples, mostly from major museums, mount them for analysis, and then do the phase verification by XRD, chemistry by electron microprobe, and then do your Raman microscopy, set data collection standards, collect spectra. All right, so how was all of this accomplished? Obtaining samples, the majority of my samples were taken from the American Museum of Natural History because I'm a research associate there. I go into the collection, open the drawers, pull specimens from the drawers, identify the target phase, and then pick off. I mean, I only need millimeter-sized grains. I don't need very much. I take it from the edges of the sample. In most cases, the sample doesn't look any different. At the same time, I ended up with quite a few samples from the Smithsonian and the Harvard Mineralogical Museum as well. All right, this is what the results looked like, and this is actually fairly early. I collected over 400 of these samples as part of this study. Sample preparation. Because I'm polishing flat, I could use the same prep for microprobe and Raman. I start out with a nylon mesh on rubber cement. And this is not just for organizing the minerals in separate spaces. I took advantage of the nylon mesh so I can lean the grains and achieve more than one orientation and non-special orientations. I avoid laying them on their cleavages and so on. When that's done, I put down a brass ring as a container, set it in epoxy, grind in, and polish. This is what the result looks like. K, chemistry, done using a microprobe down at the American Museum of Natural History. It's got wavelength dispersive, energy dispersive spectrometers, and in a lot of cases, uh, energy dispersive standardless quantitation is sufficient. It's faster. There's a lot of cases where that is sufficient to verify phase identity. Worth noting, determining the chemistry is not just for phase naming. Just like powder XID for solid solution minerals, the peaks do shift with composition. The olivines, forsterite and phthalite, a continuous solid solution between a magnesium end member, iron end member. Blue here is a full 100% magnesium end member. Green here is 66% of the iron end member. We can see the peak shifts and some peak and peak shapes. So yes, the user needs to know when they get a match, not just it's an olivine, but where in the solid solution it is. Sample preparation for XRD, grain size further reduced, and then I take a 200 to 300 micron grain. In some cases, for really fine grain materials, it's a grain cluster. Pick it up on a micro loop. This is what the result looks like. This is what a set of 80 of these pins getting ready for analysis looks like. And the reason for this particular approach is to optimize the possibility of getting only one phase mounted. Data collection is on a single crystal XRD machine at Columbia. You're running it in powder motion using Gandolfi motion. The pattern I get with this method, it has fairly broad peaks, but my objective is phase verification. So the patterns are compared to records in the PDF for phase verification. All right, so I have verified samples. Raman data collection, I have to set data collection standards. There isn't time to talk about the whole process of development that led to setting these standards, although you saw how I chose the spectral range 80 to 1400 wave numbers. Spectral resolution, I tried to stay in the 3 to 5 wave number range. Laser wavelength, signal strength is important, so my go-to is 532 nanometers, but if I run into fluorescence, I go to another laser wavelength. These are the other wavelengths I used in this work. Signal noise ratio, it's hard to quantify this as you're working on the machine, so I use visual estimation. Crystallographic orientation, I simply take spectra on multiple grains, or in some case, I rotate the sample under the instrument between data collections just to see if there is a lot of variation in relative intensity with orientation. If the answer is no, then I only submit one spectrum to the database. If the answer is yes, then I submit examples representing the extremes to the database. The instruments used, a lot of it was done on this Hariba instrument down at the Smithsonian. It's got 4 lasers. And then the American Museum got their own instrument, an Oxford Instruments, formerly Vitek. This one has 3 lasers. So I have data from 2 different research grade instruments. So now I've got Raman data, spectra. What are the metadata being submitted with these spectra to the ICDD Raman file? So for samples, name of the mineral species, locality, source, ideal formula, and the measured empirical formula. XRD, type of instrument, wavelength, and what PDF record was the best match. Raman data. And again, we want to support users' ability to make their own decisions about data collection. For each spectrum, I submit where is the strongest peak in wave numbers, instrument type, laser wavelength, laser power, resolution of the instrument, calibration method. Most of this is done, well, actually, all of this is done with Raman microscopes. So what objective was used? Exposure time. Orientation, it's not a measured angle, but is it a random orientation or is it sitting on a cleavage face is some basic useful information. All right, so what have we achieved? Raman records appeared as part of the PDF database in the 2025 release. At that point, it contained rough spectra that cover 313 mineral species and new samples that I collected Raman spectra on that covered another 47 mineral species. In process for the 2026 release this fall, 142 more rough samples, 128 more samples that I collected Raman spectra on myself, and in process for the first of many in the future mid-year releases, 54 more Raman samples, 60 more new samples from my work. And where are we going in the future from here? We're going to continue growth, continue to prioritize growth with this likely to encounter index. We're going to collect new spectra, more curate more spectra out of rough, and begin collecting spectra from other scientists from the literature, either from posted supplemental information or by writing to the authors. We're going to include a quality mark system to differentiate higher quality spectra from lower quality spectra. I'm also working on a couple of metadata, relative signal intensity and laser damage sensitivity, again, as indexes for user guidance so they can quickly decide what they're getting into with and how they're going to deal with the kind of samples are their targets. Also, plans are in place to start extending into industrial materials. We're talking about and working on procuring samples for cement phases, battery materials. And as you can see, the process begins with collecting characterized samples of pure phases where we know the phase identity, collect the Raman spectra on. Accordingly, if any of you listening in can supply pure phases that are already characterized, let us know. All right, going to do a couple of demonstrations on what you can do using the software available from ICDD. Let's start with the PDF software, the software that comes with the PDF. Again, starting 2025, there is now a button that says Raman Search. We click on that. Okay, I'm going to full screen this. We see a list, we see spectra of the record selected. We can search on the metadata, mineral name, formula, so on and so forth. We actually can do phase identification on your own spectra using this. We go over here to calculate similarity index. All right, I'm going to load one I prepared for this. I'm just called unknown A here. All right, you're presented with a window for some pre-processing. You can see the background rises steadily here. This is a continuum fluorescence effect on this sample. You also see on the left here that the spectrum suddenly takes a dive. That is not a spectroscopic feature. That's the cutoff filter cutting in close to the laser wavelength. And it's very difficult to model the background when that is included. So it's generally first thing you're going to do is to trim that out. We're going to zoom to that, hit crop. All right, hit remove background. We have a background modeling system with a couple of adjustable parameters. The default values here seem to work pretty good. We're going to remove background, and then we're going to hit import. When you hit import, the software is going to automatically calculate similarity indexes, similarities between everything in the database and the spectrum you just imported. You can see down the bottom here, it's moving through the whole database. Almost there. All right. So here we are. The top match is sillimanite. I happen to know from independent information that that's correct. You can see, again, the measured chemistry of the sample that the reference spectra came from, ideal formula, and so on. Okay, of course, through ICDD and MDI, your other choice is Jade. Let's take a quick look at what you can do with Jade. All right. Of course, Jade is designed around powder patterns, but if we go up to Start, MDI Toolkit, Raman Mineral. There we go. And one of the immediate advantages, if you look on the left here, this is the list of spectra in the folder that I have previously selected. You can see up here there are 70 Raman spectra here. In this case, the file names are based on phase identity information that I had independently determined. So these are more test cases than unknowns for some study. We have many options at your fingertips here for choosing how you're pre-processing, denoising, sharpening. You can choose from several baseline modeling routines, several search match algorithms. So you have a lot of choice here right now. Auto search is on. It thinks the toppest match here is ferrocylite. It's an Enstatite 57. So it's a little off on where it thinks it is in the solid solution between Enstatite and ferrocylite. But one of the, again, one of the things that Jade is good for is handling large data sets. And one of the things it can do is batch search. So we turn this on and this thing is going to crank through. And you can see how long it's take to do each one of these. So it's pretty fast. Here's our report. On the left, file names. On the right, the top match. The secondary matches are to the right of that. And you can see it's pretty accurate for this set. I'm going to take a quick look at one of the misses down here. You see, it says wollastonite that matched to hematite. So what's going on here? We go over here. There it is. There's wollastonite. Top match is hematite. And one of the things we see, this is the submitted spectrum, and it's got a bunch of peaks over here to the right that got matched to this broad peak in the hematite spectrum. These over here, these are all neodymium fluorescence peaks, which is what led the match scoring astray. If you look down here, you'll even see the second best match is wollastonite. And so, comparing the spectra head to head is generally a good idea to verify how good the match is. All right.
Visit ICDD.com to register for upcoming webinars and to watch previous ones.